So the second entrant from University of Leeds, if I could welcome them on, it's Debangshu, Sarkar, and Arundhuti Mukherjee for the third talk this session. And if you'd like to come forward and I don't know if you want to share your screen and do it that way, but feel free.
Hi everyone. Good afternoon to everyone.
Hello, good afternoon. I'm Arundhuti.
I'm Debangshu.
And I will just share my screen in a moment. Right. Is my screen visible to everyone?
Yeah, looks good.
Right. So good afternoon and welcome to our topic, Advancing Auditory Enhancement, Integrating Splitter with Personalized Remixing Techniques. This was our submission for Cadenza's Task 1. I would like to take a moment to thank you all for this opportunity. We are really excited to be a part of this workshop today and have already absorbed a lot of interesting observations from industry experts and all the participants who spoke before us. Today, we would like to present our take on Cadenza Task 1. We were motivated to be a part of this challenge because it gave us a chance to convert our academic learning into impactful insights and step into the area of audio processing using machine learning. It also gave us the chance to explore the vast solid groundwork that has already been laid and done in this sector over the past decade. We chose to proceed with task 1 by using Splitter to compare with baseline methods. For the first task revolving around use of headphones, we implemented enhancement methods like filters and dynamic range compression. This presentation is a deep dive into our approach and our results and observations.
Hi everyone. So let me just walk you. Just a second. Yes, let me just walk you through the environment that we made use of because we needed a lot of computational power in order to move forward with the processing. So there were specifically two environments that we made use of. The HPC environment provided to us by the University of Leeds, specifically the ARC4 environment, which had the P4000 GPUs. And we also made use of the Google Colab environment and the V100 GPUs in the Google Colab environment. And capitalizing on the parallel processing capabilities of these GPUs increased our computational speeds dramatically, and that's it.
Moving forward, I would love to introduce our model. Let's get to know Splitter. Based on background study and comparative literature, we decided to look further into Splitter, which seemed to be an interesting but a less common approach for this task. So we would like to walk you through a quick glance of what we think makes Splitter unique. Deezer is a streaming service in France, and they developed Splitter as an audio source separation tool in 2019. Splitter was written in Python and it uses TensorFlow. Having pre-trained models like UNet and being trained on Deezer's internal data sets, we believe this should give it a leverage in terms of variation and breadth. Splitter presents a unique approach of providing 3 source separation models, the conventional 4 stems, a more simple 2-stem approach, and a deeper 5-stem separation. We relied on the dynamic and adaptable nature of Splitter, and this encouraged us to explore further. Understanding the workings of Splitter and opinions from industry experts by literature and prior work shared, we decided to choose this model for task 1. Our decision was primarily driven by the promise of speed and a rich repository of music this model has previously been trained on. I'll quickly walk us through a few key points which drove us to choose Splitter for this project. We believe being integrated with TensorFlow provides a leverage in terms of customizing this model. We can add parameter tuning, scale the model up or down, and directly use the entire TensorFlow library. This helps us write less code and reuse code that has been already drafted before. Splitter also showed evidence of great demixing scores while consuming less computational bandwidth. Being trained on Deezer's international data set, we believe it arms this model with like a rich repository of varied music genres. And finally, computational speed is a great supportive factor. It was important to us that our model seamlessly made use of GPUs to process the data set, and Splitter did just that. While these were some of the key factors influencing our decision to choose this model, we were also driven by ease of use, well-structured learning resources, great documentation that was available online, and an opportunity to study a relatively newer model. Going further, we would now like to discuss our demixing approach on a zoomed out level before we can move further into the nuances of all the steps that were involved. To start with, we implemented the 4-stem configuration of Splitter. This is what we needed to produce voice, drums, bass, and others. The training data set was an input in step 2. This data set was provided by Cadenza and it was pre-separated. In step 3, we focused on loading and resampling the stereo audio tracks in a specified sample rate. And the final step applied the demixing and generated our 8 stem results. Our next section is specially dedicated to provide a detailed overview of all of these steps.
Okay, so let me just walk you through all the stages of our demixing process. Firstly, the training stage. We were provided, the main training data set was provided to us by the challenge organizers, which was a subset of the MUSDB18HQ dataset. It had 86 training songs and 14 validation songs, which span different music genres from rock to heavy metal and much more. Prior to training, each track that was provided to us was also pre-separated into stem files for vocals, drums, bass, and other components. This pre-processing step provided a rich and detailed source for the model to learn from, enhancing its capacity to distinguish and separate different audio elements. We made use of the splitter 4 stems configuration, as for our needs, we needed to separate it into vocals, drums, bass, and other elements. There are other models, other configurations for splitters like the 2-stem model and the 5-stem model, but those did not align with our needs. And since Splitter is integrated into TensorFlow, we were able to leverage the GPU resources, which significantly improved the computational efficiency during training. And moving on to the next slide. So the next stage of the demixing process was the loading and resampling of the stereo tracks. So the stereo audio tracks were loaded into the Splitter framework using the audio adapter module, which is a part of the Splitter library. We first started by creating an instance of the audio adapter using the default settings. The adapter was responsible for managing and loading and processing of audio data within the Splitter framework. The loaded audio track then underwent a resampling to ensure a consistent sample rate of 44,100 Hertz. Resampling here was crucial for maintaining uniformity in the input data and aligning it with the expected format for subsequent processing. The next step was waveform extraction, which we implemented using the load method of the audio adapter module. And then finally, for the separation process, the obtained waveform was then passed to the separator for the actual demixing operation. The separate method of the separator was then responsible for dissecting the audio into its constituent stem files based on the training that we provided to the model earlier. Moving on to the next slide. The behind the scenes of how Splitter demixed all of the stereo tracks into the constituent stem files. As we know, Splitter employs a convolutional neural network architecture, specifically a unit design, which is optimized for the intricacies of audio source separation. And it also utilizes TensorFlow, which makes use of the multiple layers of neurons that learn intricate patterns and representations from the training dataset. So the first step in this was the input processing, where the stereo tracks were loaded and resampled to a consistent rate of 44,100 Hertz. The second step was feature extraction, where the initial layers of the network focuses on feature extraction, identifying relevant patterns and structures in the input audio signals. Then the next stage was the layered unit architecture, where Splietter's neural network adopts a unit architecture, incorporating convolutional layers, activation functions, and pooling layers. And during training, the neural network is optimized to minimize the difference between the predicted output and the ground truth stems of the training dataset. And finally, in the demixing phase, unseen tracks are then fed into the trained neural network, and the learned representations are employed to predict the contribution of each audio components, resulting in the generation of the separated steps. Thank you.
Moving on to the next and the second most important step in this task, remixing. Based on our understanding of remixing best practices, we finalized a sequence in which we wanted to apply our remixing techniques. We started with NALR to remove residues or artifacts. In simpler terms, we understand this as a primary cleaning of bigger chunks of disturbances and unwanted elements. So we cast a big net to remove these elements in step one. Now we had a cleaner audio minus of external disturbances, and we implemented dynamic range compression to further improve loud and soft noises as required. This helped us balance out any segments that might have been surprisingly loud or inaudibly quiet. And finally, the Butterworth filter. The Butterworth filter was implemented to allow us to accessorize the audio further by selectively boosting or reducing frequencies and maintaining a tonal balance. The results give us our final files that will then be subjected to listening tests. We chose to reduce artifacts, balance out the odd amplitudes, and provide tonal control and support. We would like to highlight that our intention here was to apply remixing in a specific order to provide optimized remixing at each stage. The next section is dedicated to provide a detailed overview of all the steps involved in remixing.
Okay, so let me just walk you through all of the different steps we utilized for our personalized remixing approach. Firstly, we made use of the NALR prescription that was provided to us as part of the Clarity library. The NALR stage is a pivotal component which employs adaptive FIR or finite impulse response filters for personalized audio enhancement. So what we did was we applied audiogram resampling to create individualized audiogram objects for each year. And why we did this was because audiograms capture a listener's hearing thresholds across frequencies, forming the basis for personalized audio adjustments. And how we utilized the NLR class. So we employed the NLR class to design adaptive FIR filters based on individual audiometric data. The NALR class facilitates the creation of FIR filters, which is a fundamental element in shaping the audio frequency response. Then the next step, which is interpolation and linear phase FIR filters. What we did was we interpolated gains and designed linear phase FIR filters for a customized frequency response. And why it matters is because linear phase FIR filters maintain the timing relationships within audio, which preserves the original temporal structure. Moving on to the next stage of our personalized remixing is the dynamic range compression stage. So the dynamic range compression stage, we employed it because it reduces the difference between the softest and loudest parts of an audio signal. What we did is there are 4 key parameters in implementing dynamic range compression. Mainly, they are attack and release, threshold, attenuation, and makeup gain. Attack and release are time constants that determine how quickly the compressor responds to increases or decreases in signal amplitude. Threshold is the level above which the compression starts. Attenuation is the rate at which signals above the threshold are reduced. And the makeup gain is the compensation applied to the entire signal after compression. So we instantiated the compressor class and we configured key parameters that I just mentioned to tailor the compression process. Moving on to the next slide is the final step of our personalized remixing process, which was the implementation of Butterworth bandpass filters. Butterworth bandpass filtering is a signal processing technique which is used to selectively pass a range of frequencies within a specified band while attenuating frequencies outside the band. The parameters that we made use of are low cut and high cut, which basically define the frequency range of interest, order, which determines the sharpness of filters transition between the pass band and the stop band. We kept the low cut at 250 Hertz and the high cut at 18,500 Hertz and attenuating frequencies outside this range. These parameters define the desired frequency band, allowing us for customization based on the characteristics of the remixed audio. Going on to the next slide.
Sorry to just quickly interrupt. We might need to wrap this up soon, if that's okay.
Yeah, sure. So we'd quickly touch upon the evaluation metrics that we've encountered. So we implemented Haki as per Cadenza guidelines, but we also experimented with additional metrics like signal to noise ratio and signal to distortion ratio. And Debangshu can quickly touch on the key highlights of that, and we can move on to subjective evaluation.
Yes, so surprisingly, all the Haki scores that we received were consistently lower than the baseline. The reasons for this can be varied from inherent model complexity to divergence in audiogram profiles. Although it is to say that depending on the listener, the decrease in Haki scores were sometimes dramatic and were sometimes much closer to the baseline than others. For the SNR and SDR metrics, regrettably, we encountered negative values for both SNR and SDR, which is not conventional. Typically, positive values are expected with higher numbers, but this could be a result of our complex remixing approaches that we incorporated, like the Butterworth bandpass filters, or maybe dynamic range compression.
Quickly coming to the good and the promising parts of our evaluation, we were able to understand what our system looked like in terms of the listener panel. It's interesting to see that Splietter's audio quality proved to be superior in about 44% of cases. For example, if we see the areas highlighted in orange, these are a few tracks that scored brilliantly compared to the baseline systems. Keeping in track of time and future occasion, we would hope to learn more about why there's a gap between the objective and subjective evaluations. With this result, we'll move to quickly summarize what we have learned so far through this journey. We were able to implement the splitter system, explore remixing techniques, and experiment with different configurations. We had an opportunity to perform exploratory analysis and study all the concepts behind the metrics we encountered. We came to the conclusion that despite having lower Haki scores, listeners perceived our audio in a fairly good sense. If we were to have questions for our future selves, it would be in aligned with opportunities to direct our efforts to optimizing Splitter better, maybe scrutinizing each stage of the demixing and remixing better. We would love to be a part of any discussions or immersive projects that explore newer metrics to better correlate likability to machine calculated scores. To conclude, our experience with Cadenza exposed us to a whole new arena of machine learning. It was a steep learning curve, but we hope our contribution added values to the cause. And thank you, and we're now open to any feedback or suggestions.
Brilliant. Thank you very much, Debangshu and Arundhuti. We may have to just move swiftly on to the final talk of the session. But if anybody has any questions, maybe if I could just encourage people to just engage with the chat section of Teams, and we can move on to the last talk. But a big thank you to both presenters again for really interesting and detailed description of their approach.